Good morning. This is course number 3, Mate Technique or Measurement Science at the University of Twente. Monday, 18 November 2013. This is Edwin Carlin teaching the course this year from the University of Tsukuba in Japan. Today I'm going to talk about two main topics, measurement signal analysis, and the second topic is measurement signal disturbances. Much of the course today is review, so there are a lot of slides that we will go over today. Some of the material will be new to you, but it's an integrative course that provides a lot of basic information about not only measurement signals, but how to characterize them and the differences between different types of noises and interference, etc. Please pay attention to Blackboard as homework number 3 is assigned today. And homework number 1 is to be submitted to my email by 24 hours or midnight tonight, 18 November, or it will be considered late. My email address for submission of the homework can be found on Blackboard as well. If you have any difficulties in submitting your homework, please send me email directly. Okay, so we will continue with the lecture, and I will first talk about the Laplace Transform, which is expected to be a review for you. I realize that some of you haven't had much exposure to the Laplace Transform, and that's why we're covering it very briefly in the course so that you are more familiar with the basic concepts. In this course, the dynamic response of a sensor will be assumed to be linear. Therefore, it can be modeled as a constant coefficient linear differential equation, as you see in the equation represented on slide 2. So we have coefficients an minus 1, which are for the output response, and then in the input response we have coefficient b0, and then the input stimulus qi as a function of t. Now in practice, these models are typically 0, first, and second orders that will represent eventually the transfer function of our system. If you remember from lecture 2, the end of lecture 2, you saw a transfer function for an accelerometer that was a second order function representing the frequency domain of the system, and this is essentially the mathematical tool that was used to derive that transfer function. The Laplace transform converts the differential equation into a polynomial expression. Laplace analysis includes exponential analysis, and Fourier analysis is restricted to sinusoidal signals. The Laplace transform of a time signal y of t is denoted by this operator capital L on the time domain function y of t, and then the transformed signal then is a capital Y with S. And S is our variable that represents a complex number sigma plus j omega. J denotes that it's a complex variable, omega. The real component, sigma, defines the real exponential behavior, and the imaginary component defines the frequency of oscillatory behavior. The fundamental relationship is the transformation of differentiation. So if we take the Laplace transform of the differential of y of t, this is going to be equal to S times the Laplace transform of y, t, which is y of s, minus initial conditions. Because this is a time differential equation, then we have to take into account initial and final conditions depending on what is required. Other useful relationships, these are 6 examples. There are many others. Impulse, which is a direct delta function that we'll use in an example later. A step function, which is 1 over s, or the ramp function, which is 1 over s squared. A decay function, s minus a inverse. The sine function transforms into omega over s squared plus omega squared. And then the cosine function, which is s over s squared plus omega squared. So these basic transforms are quite helpful when you're modeling a system and you want to go from a differential equation to a polynomial so that you can derive the frequency-based transfer function for a system and do frequency analysis. Now, applying the Laplace transform to sensor models, we do exactly this. We have a differential equation, and the operator L is applied to the entire differential equation, which means that the operation L, the transform, will be applied to each of the individual terms in the summation of the equation. And then the transformed differential equation then can be factored with all s terms coupled in a parenthesis. Q out is the output response transformed, so now it's a function of s, and then the input response, input stimulus, Qi of s. And then from this we can then formulate our transfer function as we've seen before, which is Q output of s over Q input of s, which is then this fraction of a polynomial, which is very similar to the relationship that you saw in lecture 2 for the transfer function of the accelerometer. Now you can see that we have a quadratic equation in the denominator, and furthermore there are many tools that we can use to look at the behavior of the system based on the pole locations. Remember, when we have a polynomial, fraction polynomial like this, the poles are located in the denominator and the zeros are located in the numerator. In this case, we have 4 scenarios where we have the pole location for a quadratic equation, and both of the roots of that quadratic equation are located in the left half plane, and then we have this exponential decay. If they're both located at the origin, then we have a constant behavior. If the poles are located in the right half plane, then we have this diverging or unstable situation. Then when we now introduce the complex behavior, which gives us oscillatory behavior, if the poles, location of the poles are in the left half plane, then we'll have an oscillatory system that decays to 0, so this is a stable system. If they're located on the imaginary axis, then we're going to have an oscillatory system, not diverging or converging, like an oscillator, for example. Now, if, again, the poles are located in the right half plane, then we're going to have a diverging system, and then this is unstable. So we can use the Laplace transform not only to derive our transfer functions, but then to analyze the stability of the system and the combined exponential behavior in time, and also then we can analyze things in frequency as well. The other review that I will talk about today is the Fourier Transform and the Fourier Series. These are extremely important in all areas of engineering and science. And the Fourier Series are the basic tools for representing periodic functions, which play an important role in many applications. A function fx is called a periodic function if fx is defined for all real x and for some positive number p called the period of f of x. Okay. The Fourier transform is applied to periodic and aperiodic signals. In certain situations, the Fourier transform and the Laplace transform are the same, but not in all cases. So you'll see some similarities as you start using these in practice. For example, if the Laplace transform exists and is evaluated in the j omega, then the Laplace transform, the first equation on the left, can be computed, and then the Fourier transform on the right, where we see here that S is just simply j omega, and the actual mathematical operation is similar with the replacement of variable S and j omega. The Fourier transform is the most used mathematical function in signal processing and data analysis. It gives the tools to visualize by looking into the frequency domain signal characteristics that are not directly observable in the time domain. Extremely important. And it's used in many, many areas of engineering and science, physics and chemistry. It's used everywhere. It's a very, very important tool, which is why I think I'm giving you a short review in this course. Now the Fourier transform, as I said, is this tool to convert from time to frequency domain. This is the general definition. And equivalently, you can use the inverse Fourier transform to get back into the time domain. So you can move back and forth between these two domains with this basic mathematical operation. Now, the Fourier transform typically is expressed in frequency omega, radians per second, rather than frequency hertz. Just makes it a little more convenient. And then we have this factor of 2 pi, so the differential of omega is equal to 2 pi differential f in frequency. And then you can see that when we do the Laplace transform, or the inverse, if we want to go into t in omega, then we have this coefficient, or this leading constant of 1 over 2 pi because of this conversion. So pay attention to your units. These are some examples of properties of the Fourier transform: linearity, the product, differentiation, integration, how time delay in the time domain and frequency domain, frequency shift, energy conservation. We have 2 frequency shifts there: time scaling, duality, and convolution. Okay, those are important, and those are important tools once you're using the Laplace transform. Okay, so let's do an example. Calculate the Fourier transform of the signal v of t is time, is equal to sine omega naught t. So we just directly place our function v of t into the equation. So we take the integral of sine omega naught t times e j omega t dt over the range minus infinity to plus infinity, using Euler's equation to expand things out, because we have an omega naught and omega, and we come to this general expression, 1/2 j integration, and then between parentheses we have these 2 terms. One is positive and one is negative. What do we do with this? This looks like a standard integral. We should be able to take this quite simply, but let's go into a little more mathematical theory about what this function represents. So in science and engineering, there are many examples when an action occurs at an instant of time or at a certain point in space, and the mathematical representation of this is a Dirac delta function, and you've heard of this. So it has the properties that this epsilon, between this very, very small period of time, infinitesimally small, epsilon over 2 minus between plus epsilon over 2, then the amplitude of this pulse is going to be 1 over epsilon. Everywhere else it's going to be 0. When we take the integration of that over that region, the area is going to be 1. Okay, so the integration of that over time, and that's essentially the integration between the limits minus epsilon over 2 and plus epsilon over 2. So we can then, let's plot that. And if we look at this Dirac delta function, then it's, we plot this in the time domain, you'll see that this just looks like a pulse. And then when we take this limit when epsilon goes to 0, then this is just an impulse with amplitude 1. Okay, so what this means is that the Dirac delta function, we will see is very, very important, can just be thought of as an impulse function at a particular point in time, wherever it occurs in time t, with amplitude 1. The delta function has the following properties, where we have the delta function as the time shift of tau sub 0 is equal to the integration in the frequency domain, and then the conversion back into the time domain using the same equation. The lower equation of the two is referred to as the sampling property of the delta function, is used extensively in signal processing and signal analysis. Now we can go back to our example. Okay, if we go back to our example, then you can see that we can plug the Dirac delta function directly into the integration, perform this integration, and you see at the end of this that the Fourier transformed representation of this sign then is pi j times the subtraction of these two Dirac delta functions at the two frequencies, plus omega and minus omega. So when we look at the frequency domain representation of this, we have two Dirac delta functions at the different frequencies located in space. Now, these amplitudes are basically going to represent that we have a sine or cosine signal. Okay. These are very, very important when we're doing signal analysis. Now, we will use this later. We will come back to this basic Fourier transform concept later when we do some analysis on systems. So let's look at the Fourier series now. The Fourier series is associated with periodic signals. Any periodic signal can be resolved into a series of sinusoidal signals. The frequencies are multiples or harmonics of the fundamental frequency, and the amplitudes determine the signal shape. Now, a Fourier series is an example of the harmonics of omega naught, fundamental through the sixth harmonic. And the periodic signals may be represented by a linear combination of sinusoids whose frequencies vary by a constant integer value, that coefficient c of k. And we can compute these coefficients directly with the integration that you see on the bottom. Now these coefficients c of k are called the Fourier coefficients of the spectral coefficients of the function x of t, and they represent a measure of how much signal, or the signal strength, that is at each frequency or each harmonic, k omega. Therefore, if we want to use this technique, it's a task of determining these Fourier, these coefficients for the signal that you want to represent with the Fourier series. If the signal x of t is real, then its Fourier series representation is reduced to this equation that consists of three coefficients, a0, a sub k, and b sub k, and you can see that this is a series that spans from k equal 1 to infinity. The coefficient a of 0 is simply the average value, and when we perform this operation, you can see that we can also represent the summation with a c of k and c sub 0 or c naught coefficients, and then we have a cosine with a phase shift. Any way we do it, either way, we're going to be computing the coefficients that give us the amplitude of the coefficients at each one of the frequencies. So let's do an example. Let A of k represent the Fourier series coefficients of the following square wave. So the square wave has amplitude 1, so it moves between minus 1/2 and 1/2, and it has a period of 1 as well. So we can compute directly A of k, doing the integration, and then this comes out to be 1 over j pi k, if k is odd, and 0 otherwise. So we can plot this with these 8 representations. Okay. Now each one of these 8 computations of the Fourier transform essentially gives us a certain number of summations. So the first one we have basically just the first summation from 0, and we have nothing on our segment, so we don't sum anything. The second one we go from 1, so basically we just get a sine signal. Second one we do 2 sine signals. The third one 3 or 5, we're doing odd integers. So 3, 5, 7, 9, 19, 39. As we increase our series, so the more number of terms that we have, then we can better represent the function that we're trying to transform. Infinity will give us a nearly ideal representation of the square wave, but then the computation takes longer time. So you can represent all signals using these Fourier series. Okay, so that concludes our representation of signals using Fourier series, and also our review on Laplace and Fourier transformations. If you're more interested or you want to read more about either of these mathematical functions, just send me an email and I can provide you with more information. But for mate technique, for the measurement science course, this basic introduction will serve you well enough to be able to do basic computations. Okay, now I will move on to the next topic, signals and signal domains. And we come back to our 5-block representation of a measurement system, and essentially the signal and the signal domains are important for the first 3 blocks. Well, most important for the first 3 blocks. For our measurand, which is our input signal, but then also our converted signals that we use for processing to be able to do computation and interpretation and measurement and interpretation of the measurement that we make. So a signal, as we all know, is a physically coded information. Could be voltage, speech, earthquakes, whatever it is that we want to measure and process. And there are many different signal domains: electrical, magnetic, thermal, mechanical, acoustic. Now, I know in the electrical engineering curriculum that you haven't seen so much of thermal, mechanical, and acoustic. You should be very familiar with electrical and magnetic and electromagnetic signals. So I will give a little review on all of these basic signals, the units, the quantities, the basic governing equations for each of these different domains. These domains are important when you're making measurements. And there are many other signal domains, but it's important to, especially thermal and mechanical and acoustic, you will also use in the practicum as well. And also not only the individual signal domains, but also coupled domains when you have electrical and thermal, or electrical and mechanical, so electromechanical or magnetic and thermal. All of these can be coupled, and you can have both effects that occur at the same time. We will talk about this in doing modeling of those types of systems because they're also important to understand their interrelationships. So as electrical engineers, you all know ideal signals from your textbooks: sine wave, square wave, triangle, sawtooth. We've all seen what signals should look like. When we consider electrical signals, coding can be in energy, amplitude, frequency, phase, rise time, etc. You've seen many of these, and you are becoming experts in those different representations. Now, the sine wave is the simplest signal, a sine omega t, the fundamental frequency, plus the phase shift. It has one Fourier component only. In reality, the line width is limited by the phase noise in the modulation, so we don't have an exact Dirac delta function due to noise. Okay, our signals get distorted. Now, modulation signals, amplitude modulation, and you can see now our a sub 0 is now also a function of t. That would be our measurand that gets modulated by another signal. Phase modulation, now you see the phase term is a function of t. And frequency modulation, now you see our omega is now a function of t, and also the sine function of t. So these modulations put two signals together that coexist on the same signal, okay, for different purposes. You know this from radio and television, of course. Example sources: oscillators, continuous wave lasers, radio transmitters, sensors, etc. And we'll go over more of these types of signals with respect to their use in sensor systems. Signal levels, RMS and decibels. So the root mean square is a very important statistical measure. It's a magnitude of a varying quantity, like waveforms and noise. Most instrument equipment gives output in RMS. Okay, so you need to know how to compute the basic RMS values for different periodic signals, and you'll have some practice in this in the homework. And for noise, okay, we'll also learn how to do the RMS calculation for noise amplitude. So if we have a sine wave, the RMS value is 1 over square root of 2. If we have a square wave, if we have a triangular wave, it's 1 over square root of 3. And we will see how to do some of those calculations in the homework. The decibel is used to express power ratios, useful for amplifiers and attenuators. You can just add their values. The relative dB, 0 dBm, the M stands for 1 milliwatt, is 1 milliwatt, or 0 dBm is 1 milliwatt. Minus 6 dB means 6 dB less than 1 milliwatt. dBV relates everything to 1 volt. dB UA refers to 1 microamp, etc. So pay attention to the particular unit and how it's being used. So this is where we have our introduction to the different signal domains. All signal domains have fields and fluxes. A field is a physical quantity that can be specified simultaneously for all points within a given region. Example: pressure, temperature, electric, magnetic fields. These can be time-varied or constant. A flux, a vector field characterized by a distribution of vector fields. Electrical current, magnetic flux, velocity, fluid flow, heat transfer rate. These are all similar types of physical phenomena, and these are fluxes. So it's good to be able to relate these things: pressure, temperature, electric field, magnetic field. These are all fields, okay, and then our fluxes. And you'll see electrical current here has been represented with a J. This is really current density, but it still is not normalized by by an area. So this is really electrical current density, J. So the unit there is amp per square meter. In the electrical domain, you can see the quantities that we'll be using in this class, and you're very familiar with these: electric current, current density, electric charge, dielectric displacement, electric polarization, electric field strength, electrostatic potential, resistivity, resistance, conductivity, conductance, capacitance, permittivity. For the electric domain, we start with Maxwell's equations, where we have the divergence of the electric field is equal to the electronic charge density divided by the permittivity of free space. And this is the differential form of Maxwell's equation, and then we have the integral form, which is located just to the right of that. And then we have the rest of the equations that we use to derive the quantities for the electrical domain. Electric field is equal to 1 divided by the conductivity times the current density. Voltage is equal to the integral of the electric field multiplied by the distance derivative, the electrical resistance, which is 1 divided by the conductivity multiplied by the length divided by the cross-sectional area, current, which is essentially the current density times the area in which the current flows. Voltage is equal to the resistance times current, which is Ohm's law. And then the capacitance of a parallel plate capacitor area is the area of the plates, and d is the separation distance. Magnetic domain, magnetic flux, magnetic induction, magnetic field strength, magnetization, self-inductance, mutual inductance, reluctance, which is really like a magnetic resistance, and permeability. In the magnetic domain, we have the divergence of the magnetic induction, which is equal to 0, which is the differential form of Maxwell's equations, and then the integral form is just to the right of that. You'll notice that the divergence of the magnetic inductance equal to 0 is one of the few asymmetries in nature. And then the other 6 calculations represent the quantities in the magnetic domain: the magnetic field strength, magnetic flux, which is equal to the magnetic induction times the cross-sectional area, the reluctance, and then the calculation to look at the magnetic field strength relation to the current and the number of turns of a coil, and then the corresponding relationship with the reluctance and the magnetic flux. And then we have on the bottom right-hand corner the self-inductance of a coil, where A is the cross-sectional area, and L is the length of the coil, and N is the number of turns in the coil. In the electromagnetic domain, then we have a full set of Maxwell's equations of electromagnetism. Again, we have Gauss's law. The divergence of the electric field is equal to the charge density divided by the permittivity of free space. Gauss's law of magnetism, which is the divergence of the B field, equal to 0. And then we have the constitutive equations. Faraday's law of induction, which is the curl of the electric field is equal to the time change of the magnetic induction, or the B field. And Ampere's law, which is a curl of the magnetic induction, which is equal to the current density plus the time change of the electric field the derivative of the time change of the electric field. These basic equations on the left are the differential form of Maxwell's equations, and the four equations on the right are the integral form. We will not spend any more time discussing Maxwell's equations. You will do much more of that or you have done much more of that in the electromagnetic fields course that you took in the electrical engineering curriculum. But we will have to use some of these basic laws, electrostatics, magnetostatics, and also the calculation of some basic properties of capacitors and solenoids for some of the sensors. So knowing their basic properties of these equations is important, and also the constants, the permittivity and the permeability, and being able to use those along with the equations to calculate the properties of basic structures is important for this course. In the thermal domain, we have heat capacitance, which is similar to, think of a thermal capacitance, essentially. And then the heat is equal to CTH times the change in theta. Now, theta here is going to be our temperature, but here we also dt, this large dt in specific heat should also be theta. Specific heat, thermal resistance, thermal conductivity, and thermal convection. And we will talk more about these as we go into do some more examples. Mechanical domain, these are quantities related to distance, force, and motion, length, strain, velocity, acceleration, angular displacement, and angular velocity. Mechanical domain as well, here we have the force, tension or stress, shear stress, pressure, force moment, mass density, mass, weight, elasticity, compliance. And then Hooke's law, located on the bottom. We'll do a little bit of explanation on these later, but these are probably new. Some of these are new to you, being electrical engineers at the university. So we will go over them a little bit when we apply them to very specific examples. Then we have coupled domains. A sensor performs an exchange of information in the form of energy from one form to another, or let's say from electrical to mechanical, or mechanical to electrical, and therefore operates at the interface between these different physical domains. Now, from energy considerations, a framework using the laws of thermodynamics will be derived a little bit later in the course. We consider only electrical, magnetic, thermal, and mechanical domains in this course. But it gives you a good feeling for the interplay between these different domains. It's all related to energy transfer. Okay, now that ends the basic introduction of the different signal domains, individual and coupled. And now I will go into the description of noise interference. Any unwanted disturbance that obscures or interferes with a desired signal is noise or interference. Noise can come from internal sources that are random noise, generators, or spontaneous fluctuations that result from devices or materials. And it can be reduced but not eliminated. So these random noises cannot be eliminated. They're everywhere. Interference we define as coming from external sources. For example, electrostatic or electromagnetic coupling between the circuit and the 60 Hz power lines, radio transmitters, fluorescent lights. And then we define signal-to-noise ratio. This is a formal way to account for the transmitted signal power relative to the noise. So hopefully, if you're doing well, your signal will be larger than your noise. If it's not, then you have a problem and you have to design your sensor system or your interface components to be able to give you a signal-to-noise ratio that's greater than 1. Good rule of thumb, signal-to-noise ratio greater than or equal to 3 for sensor systems. So systematic sources, saturation of your signal, a dead zone where the input can change but the output doesn't change over a certain region. Hysteresis, if you've taken the electromagnetic courses, magnetic phenomena also can very conveniently be shown hysteresis of a system, where depending on the direction of the applied potential, if you're moving in from 0 to a plus V in, you get a certain response in V out. If you're moving from V in the negative direction, then you get a different response in the hysteresis. Loading, interface mismatches, impedance between the sensor and the readout circuit. Calibration, uncertainty in the reference values, errors during calibration or erroneous calibration values. And dynamic, measurement system response time smaller than the measure-in signal changes. So the signal can't see the measure-in changing. It's not fast enough. Okay. Random noise sources, these can be environmental, external influences. Resolution, various quantization effects that occur throughout measurement chain, potentiometer, A to D converter, sensors. Drift, slowly varying effects that cause disturbance to measurements. Noise, these are really the random noises. Device internal influences, thermal noise, shot noise, 1 over F noise, and we'll talk more about those in today's lecture. This is an example to show you a noise plot, very generalized. On the x-axis we have frequency. On the y-axis we have spectral density. And spectral density is listed in this plot as arbitrary unit, but usually it has the spectral density gives us a noise content in a unit of bandwidth. So usually the spectral density is given a function S as a function of F frequency, and it's a square of the voltage. It's really a power per hertz. Okay. Sometimes you'll see the spectral density in units of volts per root hertz or ampere per root hertz. And this root hertz is where the bandwidth, the noise bandwidth, plays a role. Okay. So in this plot, we see a few things. We see this general decrease of our signal from very high level at very low frequencies down to about 100 hertz. We see this very straight line, and you'll notice that the x-axis is in log scale and the y-axis is also in log scale. So this is the characteristic signature of 1 over F noise, this decrease in the signal as we go to higher frequencies. And then when this flattens out, then we have, this is the region of thermal or shot noise of your system. This is random, so your system will always have some basic noise content. You can't average it. It's always going to be there. This baseline noise element is always going to be there. And then you can see we have power line interferences where they're going to occur around 100 hertz or so. We get the hum and ripple and transformer harmonics that can couple into your system. Mechanical vibrations are typically less than 100 hertz or 1000 hertz. Temperature variations less than 100 hertz. Computer power supplies are up around 1000 hertz. Contact arcing, AM, FM broadcasting, you could see it in the frequency domain where you have to be careful depending on the environment where you put your signal, where you have to do your measurement. These different types of noise signals can easily be coupled into your system. So real signals always have some type of interference and noise. And typically a noise signal looks like the signal you hear with the x-axis unit of time, and then we have this very high frequency fluctuation, and we have some subscripts here of 0, E1, and E. So noise is totally random. It consists of frequency components that are random in both amplitude and phase. The long-term RMS value can be measured, but the exact amplitude at any instant of time cannot be predicted. It is possible to predict the randomness of noise, and much noise has a Gaussian or normal distribution of instantaneous amplitudes of time. Noise is caused by the accumulation of a large number of processes that each have very, very small amplitudes, so they can combine. There are three main types of noise mechanisms: random noise mechanism, thermal noise, shot noise, low frequency 1/f noise. All of these can contribute to the overall noise signal. The mathematical tools of probability and statistics have to be used to describe noise. The probability density function of an infinite number of small independent processes follows a Gaussian distribution in most cases. The important thing about noise is that its power density is unbound. There is a non-zero probability even for very large deviations. This also means that noise doesn't have a well-defined peak-to-peak value, and it has to be described with a standard deviation, which is really the origin of the root mean square amplitude. This is a Gaussian probability density function, and this is what the density function looks like. And we're really interested in this sigma value, which is a standard deviation. So thermal noise, it was first observed in 1927 and then analyzed a year later. It's often referred to as Johnson noise or Nyquist noise or white noise. And then you can see here that E1 is really the standard deviation, the probability of instantaneous value of voltage exceeding E1. Okay, so this is a histogram of the amplitudes, and they're distributed around the mean value. In this case it's 0, and this one has a standard deviation of E1. So the RMS amplitude of this noise signal is going to be E1. Now, noise power, NT, which is KT times B, B is the noise bandwidth, we're going to talk about that later, shows a flat frequency spectrum. The spectral power density, S of F, which is watts, remember we had voltage squared, is constant. Thermal noise is generated in resistors and other dissipative elements. It is a function of temperature, KT, K is Boltzmann constant. The thermal noise voltage generated by a resistor is given by this equation. V of t is equal to the square root 4 kTb. R is the resistance value in ohms, and B is the bandwidth over which you measure. So example 1, a 10 kilo ohm resistor at room temperature produces 1.4 microvolts RMS, root mean square, and a 10 kilohertz bandwidth. The noise voltage is based on a probability density function, and the thermal noise falls off at very, very high frequencies, higher than 1200 gigahertz at room temperature. This is the general characteristic of how this works. But when we're working around room temperature at lower frequencies, we always have some sort of noise signal, baseline noise that we have to work with. When working with noise voltages, it is typically easier to use mean square values. Okay, and we will come back to this concept of noise bandwidth a little bit later. So the noise property, we can use all the equivalent circuits that we're familiar with. We can use a Thevenin equivalent circuit for voltages, and then the ideal resistor if we want to make a network of these, and then also the Norton equivalent where we can have a noise current source and then the ideal resistor. So we have this resistor, it generates a noise voltage. We can separate these into a lumped model that has a noise voltage source and an ideal resistance in them. We can do analysis on these. So we can do parallel and series resistor combinations. The thermal noise equation of the resistor, Vt, predicts that an open circuit or an infinite resistance generates an infinite noise voltage. However, this is not observed in practice, as there is always some shunt capacitance that limits the noise. Low frequency noise from Vt directly affects the output noise, Vno. Higher frequency components from Vt are effectively shunted by the capacitor C. So let's look at the circuit in the lower left-hand corner where we have the noise source in series with a resistor, and those are both parallel connected to a capacitor. And the noise output voltage, Vno, is across the capacitor C. This would be open space, for example. Now, since Vno is not a phasor, we are only interested in the magnitude. Now remember that noise does not have common phase noise source, and the resistance and the impedance of the capacitor. So we can derive that, and then remember that we'd like to look at the powers when we look at the noise. So we take the square, the magnitude, the square of the magnitude. Now if we want to find the total noise energy Nt in a particular frequency band B, we can then do our calculation, and we see that the total noise energy is due solely to R and C, but in reality it's primarily due to the shunting capacitance over the noise bandwidth B, which is quite an interesting observation from the noise analysis. Now the noise bandwidth is not the same as the commonly used 3D bandwidth. The bandwidth of an amplifier or tuned circuit is classically defined as the frequency span between the half power points. Right, and we're familiar with this. Now the noise bandwidth is the frequency span of a rectangular shaped power gain curve that is equal in area to the actual power gain versus frequency curve. So we compute this bandwidth using this equation, 1 over G0, which is the peak power gain, and G of F, which is a power gain as a function of frequency. The noise bandwidth is the area under that power curve, the integral of a power gain curve divided by the peak power amplitude. Now, since the power gain is proportional to the network voltage gain squared, the equivalent noise bandwidth can be computed directly like this. So essentially we're going to take the area of the red region and we're going to fit it into this rectangular region with the same amplitude, and then that frequency width of that rectangular region is going to be the bandwidth of our system. So when we're doing calculations of these systems, then we know what our bandwidth is and we'll be able to predict what our noise from a system is. So when we have a series of resistors or capacitors or other noise generating systems, at the end, these are all going to be defined over the bandwidth in which we measure. We need to be able to define that quite nicely and precisely. Shot noise, a noise current mechanism in transistors and diodes, and it's defined as a current in this case, which is square root of 2q, electronic charge, the DC current, and again, the bandwidth. Shot noise is sometimes visualized as measuring the water flow caused by raindrops in a bucket. An example of this is a current of 1 microamp has 570 picoamp fluctuations measured in a 1 megahertz bandwidth. Low frequency 1 over F noise, it's also referred to as flicker noise, is generated in electronics and noise power and follows a 1 over F curve, as we saw in the previous spectral density plot. It is usually dominating noise below 2 Hertz for silicon JFETs to below 1 megahertz for gallium arsenide RF amplifiers. For sensors, typically, depending on the type of sensor you have, it's typically 10 Hertz and lower, sometimes 50 Hertz and lower, then you're going to have this large 1 over F noise. Okay, and so we always have this 1 over F noise where we're doing low frequency measurements that causes problems depending on what your signal to noise ratio is. In most situations, we can reduce the random noise by averaging. We can't get rid of it, but we can reduce it over a number of samples. But the 1 over F noise is an indication of a so-called random walk, and averaging does not improve it. Okay, so this is something that we need to deal with. There are ways like synchronous modulation that allow us to modulate the signal during our detection phase to a higher frequency where the 1 over F noise is negligible, and then bringing it back by demodulation later. We'll talk about these types of techniques later in the course. Some more properties of 1 over F noise. 1 over F noise is temperature dependent. It goes down with the decreases in temperature. Examples of qualitative examples of 1 over F noise. Remember to look at the log-logs representation of the spectral density and the frequency, but they typically have these types of representations. If we look at data sheets for amplifiers, 1 over an F for the amplifiers, you will see less than 100 Hertz. You always have to deal with this 1 over F noise. As we get into higher frequencies, you can see the white noise is around 8 nanovolts, and usually we like to do measurements at higher frequencies where we just have to deal with this white noise. The signal-to-noise ratio, SNR, is defined as, for a given frequency, the ratio of the signal power to the noise power, or in decibels, 10 times the log base 10 of the square of the signal voltage divided by the square of the noise voltage. The noise spectrum must be known to choose the optimum measurement frequency range. The SNR may not be constant, and modulation can be used to select the best working frequencies. There are 3 examples in the bottom. So on the left plot, we see that we choose the left portion of the plot because the signal is higher than the noise. In the center plot, we see that the signal is larger than the noise over all frequencies, so we can measure over any of those frequency ranges. And then we can see on the last one on the right that the measurement frequency, low frequencies where the signal is higher than the noise, is preferable. So we can use different methods in order to modulate where we do the measurement using modulation techniques, synchronous modulation, demodulation, and we'll talk about that a little bit later in the course. Let's do an example. So we want to do noise limit detection. We want to make a strain gauge bridge, which consists of a full bridge configuration, and the strain gauges have a gauge factor of k equal 2. The equivalent noise output voltage of a bridge amplifier, which is not shown here, is 20 nanovolts per root hertz. The bridge supply voltage, Vi, equals 5 volts, and the bandwidth over which we measure is 1 hertz, which is extremely small. So we define the gauge factor as the change in the resistance over the base resistance divided by the change in the length of the strain gauge divided by the original length of the strain gauge. Now, in the lower left-hand corner, you'll see this is a full bridge configuration. I want you to become very familiar with this. This is called a full bridge because all elements, which are shown in blue, are changing. So we have a strain gauge. When it elongates, the resistance changes. When it compresses, the resistance changes. So we can see that we have strain gauges that change minus delta R and plus delta R, and we configure them into a full bridge configuration. This is the highest sensitivity bridge configuration. And then the output voltage is basically the subtraction of VA minus VB. And you can see that you can do the calculation using voltage divider of VA and VB, and then V out is equal to VI times the gauge factor multiplied by delta L over L. And you can go through and do that calculation on your own. So what is the minimum strain that we can resolve with this system? If we now use the equation for the output that we derived, we can get a representation for the strain, delta L over L, which is equal to 1 over K multiplied by V out over V in. So we know that K is equal to 2, and we know the output noise that we're going to see is 20 nanovolts per root hertz. We know the bandwidth is 1 hertz, so we have 20 nanovolts times the square root of 1 divided by 5 volts, which is the input. So the minimum strain that we can detect with this system is going to be 2 times 10 to the minus 9. Okay, this is an example of how to do a calculation like this. So we didn't explicitly put the bandwidth into this equation, but we had this equivalent noise of the amplifier that reads V out is going to be 20 nanovolts per root hertz. It's the output of the amplifier reading it. So the output that is going to be limited by this 20 nanovolts per root hertz. Now the bandwidth of what we measure, if we have a filter on the output of this, or if we're just using the bandwidth of the amplifier, then this signal is going to grow. 1 hertz bandwidth is very, very small. So to be able to achieve a strain like this is actually quite difficult. Let's do another one. A sensor signal is 10 nanovolt sine wave at 10 kilohertz. A good low noise amplifier will have about 5 nanovolts per root hertz of input noise. If the amplitude bandwidth is 100 kilohertz and the gain is 1000, we can expect our output to be 10 microvolts of signal, which is 10 nanovolts times 1000. The broadband noise output then is 1.6 millivolts, and that comes from the gain and this very, very large bandwidth from the amplifier. So we want to be able to measure a sensor signal of 10 nanovolts, but the noise, the broadband noise output is 1.6 millivolts. We're not going to have much luck with this configuration in the measurement done. Okay, so on the output of our system, let's use a bandpass filter to try to reduce the bandwidth of our measurement. We'll choose a quality factor of 100. This is quite a good filter, centered at 10 kilohertz. Any signal in the 100 hertz bandwidth will be detected, so that you can see the filter configuration on the bottom. The noise in the filter pass band will be 50 microvolts. And the signal will also be amplified, right? It's going to be 10 microvolts. The output noise is still too hard, and an accurate measurement can't be made. Further gain will not help the signal to noise problem, because it will also amplify your noise. What if we decrease the measurement bandwidth to 0.01 hertz? In this case, the noise in the detection bandwidth is 0.5 microvolts, while the signal will be 10 microvolts. Now the signal to noise ratio is about 20, and we can make an accurate signal. But how do we get 0.01 hertz measurement bandwidth? And we'll talk about some of that later using synchronous demodulation. In some cases, there are systems that will allow you to measure over these very, very small bandwidths. But it can be difficult. So the noise is not always very easy to deal with, and it's something that in sensor systems, when we do measurements, the resolution or the limit of detection is often limited just by the noise of the system. Okay, so let's move on. Elimination or reduction of interference sources. Some examples: thermal, these temperature control and insulation; mechanical, vibration damping; acoustic, isolation from air currents; humidity, active moisture control and packaging; electromagnetic interference, shielding and grounding. An example of the mechanical damping. Now, we used to, in the previous semesters, we had a practicum exercise using atomic force microscopy, and then you could see the vibration isolation system, but essentially vibration isolation for mechanical vibrations and acoustic vibration can be handled by placing these instruments on a table that is floating. So if you get vibrations in the floor, the table where the instrument unit is sitting is isolated because it's floating on a pocket of air, and so all of the vibrations essentially get isolated from that air between the table and the measurement instrument. Electromagnetic interference is caused by radiated electromagnetic fields or conducted voltages and currents from unintended sources. The interference is produced by a source emitter and is coupled to a susceptible system, causing an error. The coupling path may involve one or more of the following mechanisms. Okay, and then an example of these: power lines, electric motors, lightning, broadcast, mobile radios. This is a little bit old. Any type of electromagnetic wave can cause interference, electromagnetic interference, to your measurement system. Now, interference can be capacitively coupled into wires in the circuit, magnetically coupled to closed loops in the circuit, or electromagnetically coupled to wires acting as small antennas. And interfering signals can enter the setup through the supply and signal lines. Coupling can also take place through common ground lines. Interference, unlike noise, can be eliminated in principle. So EMI coupling, for example, in the block diagram, we have an error source, coupling channel, measurement system. In this case, motors always cause big problems in electrical circuits if you're not careful. So you have a motor control circuit, a DC motor, and you have other circuits that do something else located in the system. These radiate quite heavily if not properly shielded, and those can radiate right into your circuit. So you have to have good shielding in your system to prevent this radiated noise from these high current or high voltage systems that can be located in the room or in the environment where you want to do your measurement. Conducted interference is coupled between components through interconnecting wires, such as through power supply and ground wires. Common impedance coupling is caused when currents from two or more circuits flow through the same impedance, such as in power supply or ground wires. Radiated electromagnetic field coupling may be treated as two cases. In the near field, E and H field coupling are treated separately. In this example, we see common impedance coupling. We have two circuits, circuit 1 and circuit 2. They're connected to a common ground impedance. Now, each circuit can have a ground current, labeled 1 and 2, which can result in two different ground voltages, ground voltage 1 and ground voltage 2. So in reality, circuit 1 and circuit 2 could have different values for the ground. We assume that it's 0, but it can be something completely different, and this is something that we do not want. Radiated EMI coupling. For exact representation of coupling, Maxwell's equations must be solved in 3 dimensions in time. Now, to avoid this complexity, we have to use equivalent circuit analysis to represent coupling. And we do this by saying that all electric fields are confined to the interiors of capacitors, all magnetic fields are confined to the interiors of inductors, and the dimensions of the circuits are small compared to the wavelengths of the radiated fields. Electric field coupling is caused by a voltage difference between conductors. The coupling can be modeled as a capacitor. So this is our lumped equivalent circuit representation of two conductors unshielded, creating capacitive coupling where the signal can get radiated onto your impedance to ground. Magnetic field coupling is caused by a current flow in conductors. Coupling mechanism can be modeled by a transformer. We have the magnetic field. So we literally get coupling. So if we're flowing current through here, we get an electromagnetic field that couples to this coil, right? And then we generate a current into this coil. So we can measure this as a transformer. Interference elimination, reduction methods, shielding, grounding, cable design, isolation, balancing, filtering. I'm going to go very briefly through these different methods. They're very powerful, and we'll do some homework on these to practice on our skills. Capacitive coupling. We have two conductors, 1 and 2. Now, we can represent this system with 3 capacitors. C12 is a capacitance between the conductors. C1G is the capacitance between the conductor and the ground. And C2G is the capacitance between conductor 2 and the ground. And from this, we can make this simple lumped equivalent circuit of the system. And then we can use our tools of Laplace transformation to represent a circuit with a transfer function, Vn being the output, the noise, how conductor 1 is going to capacitively couple its noise onto conductor 2. Should be able to derive this transfer function on your own. If we say that the resistance of our load is much smaller than this expression, then the output is just going to be a function j omega RC multiplied by our input voltage. If the resistance is much larger than this impedance, then the noise on the output is going to be a ratio of the capacitances C1, C2, C12, C12 plus C2G multiplied by V1. So how does that look? If we look at the output response in frequency, in this region omega smaller than 1 over R times C1, 2 plus C2G, the noise voltage is going to be at this amplitude. So we basically ramp with Vm equal j omega R C1, 2 V1, and then we saturate for these higher frequencies at this V noise. So that's essentially how this is going to work. So if you're working at low frequencies, obviously, then you're not going to have much coupling in this system. If you're going to be working at higher frequencies than omega, then you're going to actually induce an electrostatic potential onto V2 by current that's flowing through conductor 1. So how can we use this? We can do capacitive shielding, where we physically take a shield. It can be a mylar foil or some other type of foil to basically allow the electromagnetic field lines or the electrostatic field lines to terminate on this conductive capacitor and prevent the generation of the coupling directly to the conductor C2. So then we essentially make a new modified transfer function that you see on the bottom. And Vs now is the source that's going to be with respect to the shielding and the ground. Okay, since there is no current through C2S, the voltage picked up by conductor 2 is Vs. If the shield is grounded, then Vs is equal to 0, and their interference voltage on conductor 2 is also 0. Vn is equal to 0. You can work through that on your own to make sure you understand that. Based on the previous example, we can introduce different types of cables that have shielding to reduce the amount of coupling between conductors. So the most important one is coaxial cable. Most of you are very, very familiar with this already. It has a single conductor surrounded by a plastic layer that provides the insulation between the conductor and a braided metal shield. The metal shield helps to block any outside interference from radiated fields, fluorescent lights, motors, etc. And this is an example of the coax cable that you have probably seen many times already. Twisted pair cables consists of pairs of cables. Each pair is twisted together and the signal is transmitted to one of the pair and the inverted signal to the other. The signals are subtracted because any electrical noise is likely to affect each of the pair of cables equally, and the result is a noise-free output signal. And then we also have shielded twisted cables, and these have improved interference rejection. And this is a table showing the regions in frequency where particular cable types are most important. So coax cable, probably the most important, that is, it spreads up into the hundreds of megahertz region. So it's a good cable for general purpose use. But expensive. So you can use twisted pair if you're going to be using lower frequencies, because it's just less expensive. Then if you want to get into higher gigahertz range, then you need waveguides, and then also if you want to get into the optical domains, then you need optical waveguides, etc. Ground loops can also be a source of noise, especially when multiple ground points are separated by a large distance and are connected to the AC source, power ground, or when low-level analog circuits are used. So this is an example of a ground loop, and essentially you have two grounds on circuit 1 or 2 that create this ground loop problem, VG. And we'll have a homework problem on this so you can see. One way to get around this is to put a transformer between the two circuits. Excellent ground loop isolation. The disadvantage, limited frequency range. You don't have DC continuity between circuit 1 and circuit 2. And it can be large and expensive. Another way is to do optocoupling to break the ground loop isolation. So that's the end of today's lecture, and it was quite long with many different topics, but many of the topics that we talked about today should be a review, and the important topics that are required for the exam will be covered on homework number 2. Thank you.